Welcome again. Today we will discuss organic peroxide mediated reactions. First we will discuss Baeyer-Villiger oxidation and then we will discuss Haffley's epoxidation. So, Baeyer-Villiger reaction, this reaction is named after Adolf von Baeyer and Victor Villiger, who first reported the reaction in 1899. It is also known as Baeyer-Villiger rearrangement and popular synthetic tool for converting acyclic ketones to esters and cyclic ketones to lactones. This was the first report by Baeyer and Villiger. This was menthone, and when they treated with persulfuric acid, whose structure is like this. So, with monopersulfuric acid, they converted menthone to this lactone. As you can see here, the more substituted carbon atom migrated to get this lactone, and also they converted tetrahydrocarbon with treatment with the same acid, they got this lactone. Here also the more substituted carbon atom that is containing the methyl group has migrated. So, after this discovery, many applications and options are studied. Most common acids used was metachloroperoxybenzoic acid or metachloroperbenzoic acid MCPBA. Then peroxybenzoic acid, also trifluoroperoxyacetic acid is very commonly used. And salient features of the mechanism which was proposed by Kriege. Here the retention of stereochemistry by the migrating group. So, that is very important. If there is a chiral center, that stereochemistry is retained during this reaction. Migration is concerted with departure of leaving group, which is the rate determining step. So, there is a leaving group which is ultimately becomes acid. So, metachloroperbenzoic acid becomes metachlorobenzoic acid. That is the rate determining step, and general order of migration is 3-degree alkyl. So, more substitute alkyl migrated more, then cyclohexyl, 2-degree alkyl, benzyl, phenyl and 1-degree alkyl. So, this is important. Phenyl migrates more than 1-degree alkyl, and lastly hydrogen is there. Migrating groups should be anti-propellant to the O bond of the leaving group. This is also important, this we will discuss in detail later. So, here also the migrating group and the O bond of the leaving group, that should be anti-periplanar. Electron withdrawing group on peroxy acid and peroxide enhance the rate of rearrangement. So, if there is electron withdrawing group on the peroxy acid, then its reaction is much faster. So, reactivity order of per-acid. So, trifluoroperoxyacetic acid, this is trifluoroperoxyacetic acid, this is the more strongest in this Baeyer-Villiger rearrangement. Then monopermalic acid, whose structure is this is monopermalic acid, then monoperphthalic acid. So, this is monoperphthalic acid, then 3,5-dinitropurbenzoic acid, paranitropurbenzoic acid, metachloroperbenzoic acid, this is peroxyformic acid, then perbenzoic acid, then peroxyacetic acid, hydrogen peroxide and tertiary butyl peroxide. So, with trifluoroperoxyacetic acid, this will be the rate will be much faster. And we will discuss now the mechanism. So, general reaction mechanism for acid catalyzed reaction of acyclic ketones. Here the ketone is first protonated by the acid, and then the addition take place to the carbonyl moiety, activated carbonyl moiety to get this hemiacetal, and this reaction, which is the rate determining step. This is the rate determining step. Here what happened, this migration happens and this OH is becoming carbonyl, and then one group is migrating, it is attacking to the oxygen, and this is leaving group. So, acid is a conjugate base of the acid, or acid is the leaving group here, and then you get the protonated ester, and after deprotonation you get the ester. So, a ketone is becoming ester in the Baeyer-Villiger reaction. This is very important because esters are very useful structures. And for acid catalyzed reaction of cyclic ketones, this is similar mechanism. The cyclic ketone also gets protonated to get the oxonium ion, and then the per acid reacts 1:2 fashion to get this hemiacetal peroxy compound, and then the rearrangement will take place. So, this will go to carbonyl, and then one group will attack to the oxygen, and this will leave. After that, this lactone will form. For cyclic ketone, you get the lactone, protonated lactone, which is after deprotonation gives the lactone. So, this is also very useful compounds. This is also we just told. So, the anti-peripellinar orientation is very important. The migrating group and the O bond, it should be anti-peripellinar to each other, and this is the primary stereoelectronic effect. So, here if you see that this is the ketone, where Rm is the migrating group, and if you treat with this peroxy acid, then you get this intermediate, peroxy hemiacetal intermediate, and here this rearrangement happens. So, this becomes carbonyl, and this attacks oxygen, and this leaves. Now, if we draw like this Newman projection, and if you see on the oxygen and carbon bond, oxygen and downside is carbon bond is there. So, oxygen has 1 hydrogen and 2 lone pair, and Rm will be drawn like this, Rm, R and this. So, this carbon has 3 substituents, R, Rm and oxygen here, because CO we are looking at that bond. Now, Rm, R and OR, they will orient like this way, that Rm and this and this is anti-peripellinar to each other. Also, there is a secondary stereoelectronic effect, where the lone pair, one of the lone pair and Rm, so this lone pair and Rm, they are anti-peripellinar to each other also. So, this is very important. The stereoelectronic effects determine the anti-peripellinar orientation of Baeyer-Villiger oxidation, and then you get the ester in this case, and you get the carboxylic acid. So, per acid becomes to carboxylic acid, and ketone is becoming ester. So, this is very understanding that one oxygen is going to the carbonyl compound giving the A, and one oxygen is liberated, so that the peroxy acid is becoming to the carboxylic acid. And this stereoelectronic effect can be understood by using this substrate, tertiary butyl cyclohexanone, where there is a fluorine atom at the alpha carbon of the keto group. So, when the fluoro group is in the axial orientation, difference in dipole moments in the various conformation are minimal, because this fluorine, you can see this is quite far from the carbonyl group. So, the stereoelectronic effect is quite low here. Difference in dipole moments in various conformation are minimal and do not influence the migration of either the CH2 or the CHF group. In this case, a normal product distribution was observed, and the electron rich CH2 group migrates preferential. So, here just the electron withdrawing group effect of CHF is working, because there is no such stereoelectronic effect. The dipole effect is not a dominating factor here. Here the electron withdrawing group is migrating less. So, you get this migration more, and that is why you get 71% this product, where this group, you can see this group, this carbon has attacked to the oxygen, and when this carbon attack, then you get this product. So, this you get 29%. Now, if you put now the fluoro group in the equatorial position, what happens? Now, the CF dipole is close to the carbonyl, and anything you add, this dipole will affect. So, the dipole-dipole interaction will be important in this case. So, the conformation with CH2 antiperipellinar to the creates an unfavorable dipole interaction on the per ester with the CHF group. Because if you want attack, now this CF, this one is closer compared to the axial, which is far. So, there will be some effect on this dipole. In this case, the electron for CH group can achieve the required alignment more easily and is forced to migrate. So, this one is migrating more, this one, because you can see if this and antiperipellinar will be this one. However, when this group migrates, then this and this. So, in this case, what happens? if this group migrates, then what happens, this carbonyl groups goes down because to get the antiperiplanar, and then it will be more interaction with the CF bond will be there. But when this migrates, then the OO will be quite far from the CF bond. So, here this is very interesting, here you get this carbon atom attached to the fluorine that migrates and you get this product more and this is less. So, here when this group migrates, then problem is that then this interaction of O bond, because this comes closer to the CF bond, that interaction is more. Here are some examples. So, this is fluorobromobenzyaldehyde, 4-bromo 3-bromobenzyaldehyde. If you do MCPBA oxidation, MCPBA, that is the Baeyer-Villiger oxidation, you get this acid. So, here H minus migrates instead of aryl group. This is important. Earlier we told that pH migrates more than alkyl, more than hydrogen, but here hydrogen migrates because the aryl group is electron withdrawing. There are 2 electron withdrawing substituents. So, that is why it is not migrating, only H minus migrating here. However, when you treat this one, here what will happen, aryl group will migrate and you will get this compound, and this after hydrolysis will give this compound. So, here aryl group migrates. Here aryl group migrates compared to the aldehyde. Similarly, if you do here this Baeyer-Villiger epoxidation BBE, similarly if you use the acetophenone, what will be the product here? As I told that phenyl migrates more than alkyl. So, here phenyl group will migrate, then you get this compound. So, here a cyclic ketone, cyclopentanone, and with a 2 substituent cyclohexyl group is there. This Baeyer-Villiger condition was magnesium monoperoxyphthalate and sodium bicarbonate methanol condition. You get this product lactone, where this more substituted carbon atom is migrating. So, this is always, suppose this one, here what happens, here also this is the more substituted and this is primary, this is secondary. So, you get this compound, and this is a chiral cyclohexanone 2,3-dimethyl cis-2-methyl dimethyl cyclohexanone. This under MCPBA condition, it gives this lactone, where more substituted carbon atom migrates. Also, these groups, chiral groups, are undisturbed. There are many reports also on metal catalyzed Baeyer-Villiger oxidation. So, here the idea is that you can use stoichiometric amount of hydrogen peroxide, and you can use a metal oxide like here methyl trioxorhenium. Rhenium is a transition metal. So, under this condition you can get cyclobutanone to butyrolactone, 5-member lactone is formed in very high yield. So, what happens, this complex rhenium, this is the methyl trioxorhenium complex, this binds with cyclobutanone first, there is a coordination happens, and now this bond is peroxo bond gets break and this attacks to the carbonyl, and ultimately this after this cleavage you get the butyrolactone and this become carbonylizing, that is becoming again the peroxo bond is forming from the H2O2. So, catalyst is regenerated again and again by H2O2 here. This strategy was applied to other substrates like here bicyclic compound, was converted with that MTO 0.3 mole percent H2O2 and you get this lactone. Also there is a two mixture of products, so 87:13 overall 63% yield. Here the more substituted was the major, this was the more substituted, so this was the major 87%. Here a tricyclic compound was also treated under this condition and this compound was formed. Here though this was the quaternary center, but two electron withdrawing groups are there. So, groups containing electron withdrawing groups, the migration will be much slower, and that is why this group is migrating, this carbon is attacking to the oxygen. So, you get this product only. Here a chroman compound was used, a carbonyl group is there under this condition. Also here you get selectively this product, where the aryl group. So, this group aryl group migration. So, aryl group is migrating more than this CH2 group. This reaction also was applied in different natural product synthesis. Here a complex structure was used where many chiral center is there, and under this condition MCPBA, sodium bicarbonate, dichloromethane, you get these products selectively without disturbing any chiral center. So, this lactone is forming and this stereochemistry is retained in the product. Then trifluoroperoxyacetic acid was used for the steroid derivative, and here a carbonyl and ester group is there, and under this condition the ester group is stage, the ester group does not react under this condition, and only the carbonyl group reacts to get the lactone, and here two products are formed 4:1 ratio. One, this group, when this group migrates, that is the this product is forming, that is the major, and this one migrates slowly, might be due to the steric region, because here the chiral center is there, and that is why might be the slower. So, this compound is major and minor. So, another thing I just want to tell that if you have a compound with a double bond and carbonyl, and if you treat with MCPBA, what will happen? So, if you treat with MCPBA, it has been found the epoxide will be formed fast. So, where Villiers oxidation is slow process. So, if you use one equivalent MCPBA, then you can get selectively epoxidation. So, olefin epoxidation with MCPBA is much faster than carbonyl to ester conversion. So, when you treat here only selective epoxidation is formed. Now, we will discuss surface epoxidation. As we know, Surface, Nauri and Knowles, they shared the Nobel Prize in 2001 for the discovery in asymmetric catalysis. Surface got mainly because of his epoxidation and osmolation, that is the dihydroxylation reaction. So, today we will discuss surface epoxidation. This is mainly a primary and secondary allylic alcohols into 2,3 epoxy alcohols. Asymmetric epoxidation of allyl alcohols with tertiary butyl hydroperoxide. So, this is the peroxo compound, tertiary butyl hydroperoxide, a titanium 4 metal catalyst 5 to 10 mole percent, and generally titanium isopropoxide is used, titanium 4, and a tartarate ester ligand. Tartarate ester ligand, tartarate ester means it is should be D or L tartarate, okay. Chiral ester ligand 7 to 15 mole percent. So, there is slightly more amount of the ligand compared to the metal catalyst, and dichloromethyl solvent was used, and -10 to -40 degrees temperature you can use. Uniformly high asymmetric induction throughout the range of substitution, it is possible to get high asymmetric induction. Enantiomer form depends on stereochemistry of catalyst. So, catalyst determines the stereochemistry. If you use different compared to D, if you use the other L, then you get the other stereochemistry of the product. Each enantiomer of the tartar ligand delivers the epoxide oxygen atom to one face of the double bond. This is very important. The facial attack happens. As you can see, so if you draw allylic alcohol like this way, and if you closely look at this CH2OH group is drawn on the right, down right. So, the double bond will be drawn such a way that the CH2OH group will be down side and it is right side. Then what will happen? Then D minus tartarate like diethyl here will react from the top face and plus tartarate will react from the down face. And if you draw the alcohol, allylic alcohol, suppose if you give a rotation, then what happens? The CH2OH group comes this side, R2 goes to that side, R1 goes to this side, R3 goes down. So, this CH2OH group we can tell it is down left. So, this carbon is down, this is top down, down left. Under this geometry, the plus will react from the top face and minus will react from the down face. So, this is very important to determine the product structure, the epoxide product structure. So, this is very important. If you draw right side down right, then minus will attack from the top face and vice versa, and if you write like down left, then the plus will react from the top face and minus will of course react from the down face. And this is again this what we discussed, that this substituted allylic alcohol can react, and when this orientation, then plus will react from the top face and minus will react from the down face. And if we draw like this compound, so if you see this compound, what happens? This is down carbon, if we draw like this, and this is left side. So, the plus will attack from the top face. So, this way we can see this compound. So, plus will give the epoxide from the top face, it gives 86% E, and minus date it gives reaction from the down face. As you can see here, the down epoxide is forming and it is giving 86% E. This epoxide can be written like this also, there is no harm. Substitution patterns, there are different substitution patterns is there, like mono substituted, di substituted, tri substituted, tetra substituted. This was 2 di substituted, this is tri substituted, this is also tri substituted, and this is Z di substituted. So, Z di substituted olefins are the least reactive and selective. So, if you have a Z di substituted like this allylic alcohol, then the reaction is very sluggish and also less selective. Here are different substrates are there with different substitutions. As you can see, when no only simple allylic alcohol is there plus DIPT. So, this is CO2 isopropyl. Okay. So, this is the CO2 group with OH group here, and this compound gives 90% E of the product. When phenyl substitution is there, then the E enhances to 98%. When there is a, so one carbon atom of the olefin is disubstituted, then also you get high enantiomer selectivity, also the reactivity is very good, 88%. When there is a cis alcohol now, this is the cis olefin is there, then in that case you get the E is lower, 86%. And when there is tri substitution, but this is still trans, the more substituted phenyl and CH2OH group they are trans, so you get 98% E. However, when there is cis, so this is the CH2OBN and CH2OH, they are cis to each other, that is why the E is lower, 80%. And this is very important when you have the other olefin and this olefin. So, allylic olefin only reacts under this condition, and this double bond is unreacted, and also you get 91% EE. So, this is geraniol. Similarly, this compound can be seen that with 5 mole percent titanium isopropoxide, 7.3 mole percent plus date, 4 angstrom molecular shift, DCM minus 40 degree centigrade, it will give the minus. Epoxide will be from the down phase, because here we have drawn like this down right. So, this was the right side, and now the plus date will come from the down phase. Similarly, if you use the minus date under the same condition, 5 mole percent titanium isopropoxide, 7.3 mole percent minus date, you get the top, the epoxy group comes from the top side. This is a conjugated diene, as you can see, it is very important. The conjugated diene is there, and under this condition, this double bond is unreacted, and you have to use more equivalent here, 1 equivalent titanium isopropoxide, 1.2 equivalent of minus date, also 4 angstrom molecular shift, dichloromethane minus 25 degree centigrade. Under this condition, only you get this alcohol. Since this is jet, the enhanced solubility was slightly low, 86%. This cis trans can be also explained by this same compound, the trans isomer and the cis isomer. So, trans isomer with 5 mole percent titanium isopropoxide, 6 mole percent date, 4 angstrom molecular shift, dichloromethane minus 10 degree centigrade, it gives this compound, because we have drawn the right side. So, plus will come from the down phase, and you get 94% E. And when the cis allylic alcohol was employed under the same condition, here the E, the same alcohol is means the from the down phase only, but the E is only 83%. So, what is the mechanism of surplus epoxidation that we can discuss? So, first step, the minus here minus DET, diethyl tartrate is employed, and titanium isopropoxide is there. So, first what will happen, this substitution reaction will happen, 2 isopropanol molecule will eliminate, and you get this titanium tartrate complex. So, this is very important. Titanium metal comes with the ligand. Now, the metal center is chiral. So, now a tertiary butyl hydroperoxide again will attack to titanium, and another isopropanol, this is isopropanol molecule will eliminate, you get this compound, where there extra binding of this oxygen and this ester oxygen also is possible to titanium. After that, since one isopropoxide is there, another substitution from the allylic alcohol will happen, and this will eliminate another molecule of isopropanol, and your substrate is now bound with the titanium. So, here you can see a ligand is bound with titanium, your peroxide is bound to the titanium, and your substrate is bound to the titanium. So, all three are bound to the titanium, and now this desired epoxidation will happen, because this metal center is in the chiral environment. So, the facial selectivity will happen, and you get here from the top phase only, and you get the after treatment of the isopropanol will come, because which was eliminated will react here now. After this desired reaction happens, then you get your product, and this is the derivative is formed, where one isopropoxide is there, and now again one isopropanol will react. So, it will generate the tertiary butanol, and this is the pre-catalyst, that is the form. So, titanium ligand complex is formed. So, here we can see this your ligand and titanium are getting regenerated, only your peroxide is getting to the tertiary butanol. So, that is why the peroxide we have need the stoichiometric amount, other things we can use in the substoichiometric amount, titanium catalyst as well as the ligand. Effect of other chiral substituents. So, this is a chiral compound where the chiral center is there far from this, and allylic alcohol motif is there, and tertiary butyl hydroperoxide and titanium isopropoxide condition, you get these two products which are diastromeric to each other, because there is one chiral center and another chiral center is here. So, you get two diastromeric products. Now, since there is already a chiral center, the chiral center also can influence the geometry of the products, and this was observation that when you use without catalyst, then you get this is measured 2.3:1. So, this was 2.3 and this was 1, this was the ratio, and when we use minus DIPT, then it becomes 90:1. So, this gets dominated mode. So, this is actually match case. So, here you get 90% and it is 1%, and now plus DIPT you get 1% this and 22% of this one. So, that means here the catalyst is operating, but this was a mismatch case. That is why you are getting slightly less ratio. So, what are the features of this? Products are diastromeric. Sense of induction is dominated by the catalyst. So, catalyst is controlling, catalyst can reverse also, see here 2.3, when you use plus DIPT, that time you get this one is the measure. The C4 center reinforces and erodes this in matched and mismatched cases respectively. So, in this case reinforces, because already without catalyst this was the measure. So, catalyst reinforces, that is why you get the better ratio of the measure product, and this case it is erodes, so this mismatch case. Now, chiral allylic alcohol. So, if the chiral center is present on this CH2OH, what we have seen so far, there is no substitution. Now, if your chiral center is here, so here if there is a substitution, and if we CH2OH group, that CHOH group if we draw in a plane, then what happens? The R group, that is the substitution, either we can draw up or down. So, this will be one chiral compound where R is up, and this is one chiral compound where R is down. Now, the question is whether the reactivity will be different or not. Earlier what happened? We have the plane and both sides were equally possible. Now, here suppose in this case the top face is blocked by R. So, as we know that if we keep CHOH in the down right side, then minus tartarate reacts only from the top face. Now, minus tartarate reaction on this one will be slow, because the top face is blocked, and minus tartarate under this orientation can react only from top face. So, this reaction will be slow, because the top face is blocked by R group. On the other hand, if you see the down phase hydrogen is there. So, it is no, like earlier it was no problem, because substitution is on the top side, it is blocking. So, down phase is open. So, the reaction with plus tartarate will be much faster. Similarly, if your chiral compound is such that the R is down, then what happens? In this case top phase is not blocked. So, there is no problem of minus tartarate attack. So, again I am telling, when we draw like this way down right side, then only minus tartarate can react from the top phase independent of substitution. Now, if the substitution is there, the reaction from the top phase will be fast, but down phase by plus tartarate will be slow, because down phase in this case is blocked by R group. This is a clear example of this compound, chiral secondary allylic secondary alcohol. If you see, there is a cyclohexyl group is there, and if we draw like this way, the OH group in the plane and this is up down. So, in this case the top face of the substrate is blocked, and plus date means this one can react from the down phase. So, this reaction will be very fast if you give the plus date and you give the down epoxide, and this epoxide is minor case from the top phase. So, this reaction will be much slower. Now, if we have a plus date and same date we did not change, but we change the alcohol now, the alcohol this cyclohexyl group now in the downside. So, this is the case, and if you use same date plus date. So, what will happen? If you have date is fixed, your structure is fixed. So, what will happen? It has to react from the downside only, but the reaction will be slow. So, the reaction is slow and you do not get mass selectivity. Here 62 and 38%. So, this is down and this will be actually up. So, these two products are formed, but the ratio is not good. Here 62% you get and 38%. So, in this case there is a option the plasdate to react from the downside, but here the downside is blocked. So, that is why the reaction is much slower and you get mixture. So, this idea was extended that chiral kinetic resolution. So, kinetic resolution is a reaction condition where 50% of the starting material reacts and 50% starting material does not react. So, this was the idea that if you have a racemic alcohol, whether one enantiomer reacts and another enantiomer does not react. Because as you have seen that if plasdate is there, if you have a specific alcohol, then the reaction is one case is fast, one case is slow. So, this idea can be used in the kinetic resolution when you start with a racemic alcohol. So, as you can see, if you draw like this way, the left side alcohol is there. Now, what happens? The top face is blocked and plasdate this reaction from the top side, because under when we draw CHOH in the left side, then plus will attack only from the top face, but this will be slow. On the other hand, when R is down, then this will be much faster. So, this two alcohols, when this is the racemic alcohol, the racemic alcohols are there, because racemic means this is 50-50 present. So, 50%, that means this isomer, this alcohol will react much faster with DET and this will be much slower. So, this will be unreacted and this will give the chiral epoxide. And this rate can be K relative can be calculated by reaction of K fast by K slow. If we divide, here the products are diastereomeric, as we have seen earlier. Using this half-less mnemonic contact between C1 substitute R. So, here and the catalyst predicts the slow reacting isomer. So, if we know the facial orientation of R, we can tell which side is blocked and whether rate attack will be slow or fast. With the exception of Z disubstituted allylic alcohols, K relative generally greater than 25. So, if you have a substitution, then it has been found with except Z disubstituted allylic alcohol K relative greater than 25. And when K relative is 25, the E of unreacted alcohol is essentially 100% at 60% conversion. So, this tells if K relative is equal to 25 or higher than 25, then there a kinetic resolution possible and high enantiomer selectivity for both alcohol as unreacted alcohol and the epoxide products can be obtained. Allylic tertiary alcohols are not successfully epoxide under subless condition, because when there is both side, if there is a substitution here also, then both face will be blocked. So, the reaction will be much slower. So, generally allylic tertiary alcohols are not successfully epoxidized under subless condition. Some extra factor may combine for high selectivity, like disubstituted olefin is more reactive than monosubstituted olefin. The K relative around 1000. So, disubstituted olefins react much faster than monosubstituted olefins because of the electronic nature. So, this is an example of kinetic resolution. This is a chiral allylic secondary alcohol. This is racemic, and here this orientation is on the other. So, we have to draw, if you want to draw the epoxide, we have to draw properly, and this CHOH we have to draw in plane, and this will be above or down the plane. And under this plus DIPT, tertiary butyl hydroperoxide and titanium isopropoxide condition, you get this product starting material, R alcohol is unreacted under this condition, and 49% yield you can get 99% enantiomer selectivity, and S alcohol only epoxidized under this condition. So, this clearly tells one isomer is reacting and other isomer is blocking one phase, so that plus DIPT cannot come to react. So, that is why this on the R alcohol the reaction is not happening. In this case, here one equivalent was used, another secondary alcohol. Here one equivalent titanium isopropoxide and one special peroxide was used. 1.2 equivalent minus DET, 4 angstrom molecular shift, dichloromethane minus 20 degree centigrade, you can get 96% EE and 45% yield. That means, the other minus alcohol unreacted, that one did not epoxide under this condition. This is an example, that is what we told, that disubstituted olefin is more reactive than monosubstituted olefin. Here is an example. So, if you start with this racemic bis-allylic alcohol, this one, but if you see the substitution here, this is monosubstituted, but this double bond is disubstituted. Now, under minus DIPT condition, and if you stop the reaction at 40%, then you see only the more substituted olefin has reacted. So, this gives the epoxide and this is this double bond unreacted. So, 40% conversion, on the 40%, 70% you get the product and 95% enhancer selectivity you can achieve. The surface epoxidation was utilized in many natural product synthesis, because you get the epoxide. Now, epoxide can be opened, and also the allylic alcohol that can be converted to aldehyde, and then Huttig reaction, hydrogenation, many reactions can be carried out, and the functional group you can enhance different, you can put different functional groups and you can get many complex structure. So, this was an application. So, here this olefin allylic alcohol was TMS substituted olefin, here is there, and this also allylic alcohol. So, under this condition, this gives the downside minus DET condition. So, here we have to reorient this compound, so that we can predict, we have to draw like this top down left or right side, then we can predict minus DET. So, if we right side, then minus DET comes from the top phase, and then you can get this epoxide, and after protection of the alcohol you get the mesetyl, this is methane sulfonine chloride, O-methyl compound, O-methyl, and now treated with one naphthol under basic condition, the OH reacts here, the methyl group, and substitution reaction happens, and then you get this compound. Then this TMS group was deprotected with tetrabutyl ammonium fluoride to get the epoxide, and this epoxide then opened with isopropyl amine, because as we know the SN2 reaction on the unsubstituted, on the terminal carbon will be much faster than the internal carbon, and less substituted carbon the attack will happen, and that is why you get this amino alcohol. Also, it was applied in pheromone synthesis. Here, however, cis alcohol Z olefin was used with a long chain, hexyl group is there, and here also it is very difficult to predict, but if we rewrite the molecule, then we can tell the minus DET, if it is from the right side, will come from the top phase, and you can get the epoxide. Here the enhancer selectivity might be slightly lower, because this is Z olefin. And now, PCC oxidation will give you aldehyde. PCC we have already seen, pyridinium chlorochromate, without affecting the epoxide you get the aldehyde. Then the Huttig olefination will happen with this ylide, and here actually you get the cis trans mixture. Then selective hydrogenation will be carried out to hydrogenate the double bond, and you get only the epoxide, which is called plus disperture, which is a pheromone. So, this strategy can be applied in other cases also. So, if you have a allylic alcohol epoxide, then the alcohol can be oxidized to the aldehyde, and then Huttig reaction, and then hydrogenation will give a saturated CC bond, and we can get many more structures. Application in synthesis, L-hexoses. So, here this was the starting material, disubstituted olefin is there, and you get, because this is trans, so you get high enhancer selectivity, and plus DIPT, because we have done on the right side, lower right. So, what will happen? The plus will attack from the down phase, you get the epoxide like this. Then thiophenol under basic condition was treated. So, this spine rearrangement happened, this alcohol reacts here and terminal epoxide will form here, and now the thiophenol will react at the terminal carbon of the epoxide to get this diol. After 2,2-dimethoxypropane, we can rewrite this. This was zigzag conformation. If we do like this, then this alcohol will be cis and you get the ketal protection. After that, the MCPBA, you get the sulfur oxide here, and then acetic anhydride sodium acetate. This is Palmera rearrangement. You can get this acetate. So, what happens here? Sulfinium, carbon double bond sulfinium bond is formed, and after that the acetate reacts there and you get this compound. This compound can be converted to potassium carbonate methanol condition. Here the oxygen is also rearranged to get the syn compound. Zigzag it will be syn actually, and in diol condition you get the aldehyde. Horner-Walseth olefination reduction and asymmetric epoxidation provides an iterative route to synthesis of polyols. So, this compound can be easily obtained, this allylic alcohol from a aldehyde. First, you have to do Horner-Huttig olefination, you get CH2CO2 CH-CO2 and that diol reduction will give you the allylic alcohol, and Sharpless asymmetric epoxidation will give this epoxy alcohol. Another application is Venustatriol. Here this farnesol was employed as the starting material, and as you can see the ethyl CH2H group on the right side. So, minus date comes from the top side and you get this epoxide written like beta top side, and now this epoxide can be converted to this tetrahydropyran motif. And then again another Sharpless epoxidation condition can be employed, though there is no allylic alcohol, but this CH2H group might help to coordinate titanium ligand, and then you can get also selectively this epoxide from the downside, and this after many steps this can be converted to this bromo compound. Another cyclization happens here. Also the geraniol was converted similarly with titanium isoprene minus date, and since this was left side, so minus DET will come from the down phase. So, this down epoxide is there, and this can be converted in many steps to this one. Here is a OCH2O is there, acetal motif, and then this reaction happens. So, here you can see this nucleophile, this is electrophile cyanide. So, after reaction you get carbonyl, and that can be reduced to alcohol. You can see this is the alcohol here. This diastereoselective reduction might be, and this bond was breakage, and you get the two alcohol here, tertiary alcohol and secondary alcohol. So, oxidation where cyclic ketones are converted to lactones and acyclic compounds converted to esters, and we have seen the migrating group is antiperiplanar to the OO bond which is leaving, and this migrating group also we can predict the 3-degree alkyl is more than 2-degree alkyl, than phenyl, than 1-degree alkyl. And Sharpless asymmetric epoxidation of allylic alcohols, we have to draw in proper orientation. So, CH2OH group is, if it is in the down right side, then minus DET will come from the top face and plus DET will come from the down face. Similarly, if it is drawn down left side, then plus DET will come from the top face and minus DET will come from the down face. And after predicting this geometry, we can write the epoxide structure. Also, we have seen that if there is a chiral center on the alcohol's carbon center, then the facial selectivity will happen, because then one face will be blocked, and we have seen that the chiral alcohol, if it is R or S isomer under plus DET, one will be selected when it is match case and other will not form the product, or it will react slowly. And this was exploited in kinetic resolution experiment, where racemic secondary alcohol was converted one isomer to the product and other enantiomer in the starting material. Thank you.